Alright, hi you guys and welcome. Today we'll be talking about derivatives and antiderivatives and where they actually come from. Okay, now derivatives and antiderivative actually come from the old idea of how do I deal with a non-classical shape and actually find the slope of it at a certain point. So in other words, we take a curve that looks like this. Okay, now we know what the curve looks like. It's going up in both directions and everything. But then I have to ask myself, okay, at this point, what is the actual slope of that point? Okay, now finding slope at one point is ridiculous because slope formula is actually you take the two y coordinates and you subtract them, and then you take the x coordinates and you subtract them and you divide them, and it's that simple. So that's where they started to come up with the idea of, okay, what if I pick 2 points, okay, and still keep in mind that my original point is down here. Okay, what if I take 2 points and find the slope of a secant line, and then do the same thing again and again and again, and until I get to almost that point. Okay, and this is where actually limits actually lead us into the idea behind it, and I'll talk about it. Now, what it is actually it's the derivative quotient, okay? And the derivative quotient of the secant line is actually used following this. Alright, so the secant line slope would actually be the function at h, x plus h, minus the function at x. And remember, these are just the y coordinates. And then you would take the x coordinates, which would be x plus h, and then minus x. Well, x minus x turns into nothing, so this is why there's just an h on the bottom. So the actual function is that you take x plus h and you plug it in, and you take x and you plug it into the function, and then you subtract the 2 on top. Now, if you divide everything by h, there should be an extra h in there. You'll find the actual secant line slope, and that will tell you the slope. Okay? Now, here's the thing. As they get closer and closer to each other, this distance or this number should go down and down. Okay? Alright, and so here's what we're going to do. The tangent line slope. Now the tangent line slope is actually the limit as h approaches 0. So in other words, as we get closer, the two secant points get closer and closer to each other, the discernible x change in x gets to be nothing. So that's why this goes down, and since the change in h becomes nothing, this becomes 0, and we need a limit because we can't divide by 0. So that's where we actually work up with. Okay. Now this is also known as the derivative. So f prime of x. Okay. And that's another way of rewriting this whole entire part of just working with it. And there's a lot of actual really cool rules. Okay. Okay, so let's find the tangential line slope at any point. So what we're going to do is the first thing you do is you find f of x plus h. This is probably the easiest way to do this. And then you do f of x. F of x would actually just be the same thing. So this is f of x right here, because if I plug in x, boom, I've got that. Now if I plug in x plus h, it's going to be looking like this, which turns into this big mess. Okay, but basically if I just subtract this one from this one, it'll all start to make sense. Okay, so literally I'm going to be taking it and subtracting it underneath. So 3x squared, let me see, minus the 2x, and then plus 10 right here. So I'm actually minusing all of this. Okay, so I'm minusing practically all of these as I work with it. So what ends up happening is that these all cancel out. Okay, and I'm left with this. So the difference quotient is actually going to look like this. On top, it's going to have a 6xh plus 3h squared minus 2h. Okay, and it's all going to be over h. Now, if you notice something really unique, oh, they all have an h. So what you can do is you can either factor out an h and then cancel it out that way, or you can factor out the h right there And voila, here's the formula to finding, and I'm going to put them in order. You'll see why in a second. Of actually working with this. Okay. Now, if you remember, the tangent line slope is the limit as h approaches 0. So as h approaches 0, this approaches 0, so this doesn't exist anymore, but the rest of it does. So the actual formula to find the tangent line slope at any point is 6x minus 2. Okay. So if I wanted to find the point at x equals 3, the actual slope would be equal to, I would plug in 3 in that, so that's 18 minus 2, so that's 16. So the slope of my tangential line at x equals 3 would be 16 right there. And it's really kind of cool to actually figure it out. And the actual point you could actually figure out is you plug in 3 back into here and you would get the y value. So you know at point 3 comma, let me see, what is that? So at the point 3 comma 31, the slope of the tangential line is going to be 16, which seems pretty steep, but we actually found the slope of that by using the tangential line slope. Now this is called the difference quotient, and it just works out great. So if you ever have any doubts in finding the tangent line slope, if you use this formula, even when you get into calculus next year, this will always work. But like with anything in math, there's little, not shortcuts, but there's actually some pretty cool rules that you can actually do. All right, so constant rule, if we are trying to find the derivative, and basically here, long story short, before I get started on that, this is all differentiation. Okay, differentiation is just explaining, okay, how do we find the formula for the tangential line slope at that point. And there's some really cool rules. So if you're ever finding the derivative of a constant, okay, so in other words, if I'm doing, let's say, f of x is equal to 4, okay, then the derivative of f of x is going to be equal to 0. And this is always going to be true for any constant. So I could actually change that to c, and we're going to use c just for the constant. Okay, now the power rule is if f of x is equal to x to the n power, then if I do the derivative of it, oops, x, there we go. It's going to be n times x, but raised to the n minus 1 power. Okay, and that's a really cool thing. If n doesn't equal, I think, what is it, negative 1? Yeah, negative 1. Yeah, if n doesn't equal negative 1, there's actually a different rule you have to use for that one. Okay, so if I'm finding the derivative, now that's the power rule. In other words, you just bring down the power. And if you look at the last problem, okay, 3x squared, if we use the power rule there, we're going to get 6x because you bring the 2 down, multiply by the 3, and then you change that to a 1 power. And then this was a 1, so we multiplied the 2 and a 1, and then we change this to a 0 because we did 1 minus 1, so this is technically x minus 0. So it's actually really kind of cool how the power rule works. Now the reason why the constant disappeared and I didn't have the 10 anymore was because that's a constant, and the derivative of a constant is actually there. And technically you're only doing this on each function once. So if you're doing it on a sum, so if you have f of x and then plus or minus, oops, g of x, okay? In other words, you could just basically take the derivatives and add them together. It's totally up to you, and that's why we were able to do that on that last problem. All right, now there's a couple more rules for actual differentiation that I want to show you so that you're ready for calculus. And it's the product rule, the quotient rule, and the chain rule. But I'll show you at the end after I show you antiderivatives. Okay, now we've done derivatives, and they find the tangential the equation to find the tangential slope. Okay, Now we're going to go work backwards. What if we're given the tangential slope equation and we have to work backwards to the actual original function? And that's called antiderivatives. Okay, and they have their own specific set of rules. Okay, antiderivatives are working backwards, so we'll use some notation. So the original notation of derivatives is f prime and g prime. Then capital F of x is the antiderivative. Okay, oops, and I forgot to add something to each one of these. There we go. Okay. All right, now, when you're working your way backwards from this, if you remember the constant changes to 0, well, if we're going from nothing to something, then, then it becomes x plus c. This c is some number that might exist, and you'll actually find methods later on how to find it out. But usually when you do an antiderivative, if you put plus c, it represents some number that could have been a constant that was there. Like, for example, if we're working our way back from 6x minus 2 to the actual function, we need to understand is that there's a constant there, so we need to represent that as a plus c. So we would go 3x squared minus 2x plus c. Okay, if we didn't know that was a 10 already. All right, now the power rule is kind of cool. If the derivative, if the differentiated function is x to the n power, then the antiderivative is 1 over n plus 1 times x to the n plus 1 power plus c at the end. Okay, and this is just a beautiful thing. It just works out like this. So, like, for example, if we were dealing with 4x to the second, okay, then it would be 4/3 x to the third would be the actual antiderivative, and that's the cool thing about it as you work with it. So you take this, you add 1, you put it underneath the fraction, you times it, and you get this, and that's why we divide by 3. Okay, and then the sum and difference rules for antiderivatives is the same, is that if your two derivatives add or subtract together, then their antiderivatives add or subtract together as well, plus a c. Okay, now the product rule and the quotient rule and the chain rule are actually really cool in that they help you find the product, the derivative of a product, the derivative of quotient, and the derivative. And the chain rule is actually if you have a function inside another function. All right, now taking a look at the product rule, I've defined two functions, f of x and g of x, and we're going to go ahead and do the product rule differentiation. So if we're differentiating f of x times g of x, we'll take the derivative of the first function times the second function regular plus the first function regular times the derivative of the second one. So here's how it would actually look like. Derivative first would be 6x times 2x minus 7 plus 3x squared times 2. Okay? And it would be pretty much that simple. The derivative of the second is obviously going to be 2. So if you'd like, you can actually write it down here and write out the derivatives and be able to see it real fast. So 6x and the derivative of the second is just going to be 2. Okay? Now, if we wanted to do the quotient, it would look like this. Now, the quotient is the same, except it has a minus sign, and then you're dividing by the function, the second function squared on the bottom. So it's going to look like this. I went ahead and simplified it, where this is just now 6x squared now. And then I really don't want to multiply that out and just figure it out. Just leave it as is. It's kind of cool. Okay, now, the chain rule is almost like the derivative of a composition of functions. So if g of x is inside f of x, you take the derivative of the outside function, and then you plug the g of x originally in, and then you times it by the derivative of the inside function. And this is what it would look like. Okay, so the derivative of the outside function would be the 6x, but then I take the x and I replace it with g of x. So I basically put this into here. Okay, so that takes care of that first part. Now the second part is just the derivative of the outside, and the derivative of the outside, or the inside function, which is g of x, which would be just 2. So that's where I get the 2 from, and I just multiply them together, and that's it. Okay, so that would be the chain rule of this bad boy right here. Okay, all right, that's it for all the rules of derivatives and antiderivatives that are in the beginning.